Swayam Prabha. Digital India. Educated India.
Hi, so welcome back. So we spoke about DNS the last time, direct numerical solution. So we spoke about DNS last time, and I think while we all like the DNS to be, the complete solution of a turbulent flow with all scales of motion being resolved, the problem arises that we actually do not have sufficient computational facility, which meaning that our computers are not good enough. Okay, so let me discuss that a little bit. Okay, and what exactly we do to sort of overcome that. So let's talk about that a little bit. Okay, and see if we really have how far the DNS can actually be implemented, and what's the kind of hurdles that we're looking at, and if we take other if you make sort of adjustments to the DNS, or we tweak DNS, at several places, how physical or unphysical they are. Okay, so let's discuss that a little bit. Discuss that in today's class. Okay, so essentially, what I'm trying to say here is that the computational cost, right? Okay, now we understand that in a turbulent flow, right, what are the things that we need to look at? This is going to be a numerical solution. So what are the things which are going to govern whether, my computer is going, which is going to govern the capacity of the computers that we're going to use, right? Now, number one is the domain size. I think that's right off the board, right? So is the domain size. Now the domain size should be how big? So the domain size obviously should be big enough so that it can hold the large eddies, right? So I'm going to write those down. So domain size, number one is the domain size. So this should be large enough so that it can it can hold the large eddies, right? Then the grid spacing, right? The grid spacing basically say delta x, right? Now, what are the smallest scales? What are the smallest scales? Those are basically where dissipation is happening, right? Now that should be small enough so that I can account for those, right? So in the sense I should be discretizing it, discretizing the domain in such a way that I have the zone where the dissipation modes are happening will also be discretized. It doesn't become just non-discretized, or doesn't become just a part of the domain which doesn't have too many too many grids for that matter, right? So we need a grid which will sufficiently discretize the smallest length scales, which is where dissipation modes are happening, and they will correctly represent that, right? So in the sense that delta x has to be small enough, right? Domain size, let's say L, has to be large enough so that it will be able to contain the large eddies, and the grid size delta x should be small enough so that it can account, it will be able to account for the small scale motions happening in the dissipative range. I think that's what we're talking about. Now next is delta t, right? So that is the time spacing over which the iteration or your solution is going to advance, right? Now this depends on what? Well, this essentially will depend on how accurate you want, right? Meaning that if you're looking at a time scale, then what is your capacity or at what intervals you want to look at it. Right. Now, there will be differences at even the minutest of delta t that you can take, but I think what we are talking about here is it's not up to me. If possible, I can maybe I'll take delta t is equal to 10 to the power minus 4 for that matter, 10 to the power minus 6 for that matter, right. But I mean, what sort of a solution will I get? So I have to be judicious because I am limited by my computing facility. I think that's where we are stuck right now. Okay, so let me write those the points that I just said, and then we'll talk further. Okay, so number one is the computational cost. So first of all is resolution requirements. Okay, so what we're talking about is resolution requirements, right, domain size, should be large enough, right, to represent the energy containing motions, largest eddies, right. Okay. The grid spacing should be small enough to resolve dissipative modes. Okay, and time stepping, right, should consider, will basically depend, right, on numerical accuracy. Right, and in what I know as the condition number of an iterative procedure, or what is the way it is represented in Book of Pope, which is a current number, whatever. So basically, your delta x by delta t, right. Now, this will always have a limit, because for your iterations to be stable, right, you just cannot do whatever. So this ratio also needs to be maintained, right. So that will depend on the kind of iterations one is trying to carry out. Okay, so that's basically the resolution requirements. Okay, now because of this, right, now what happens is that it is essentially it's a very high cost of DNS. So, basically we are saying that we are looking at the largest eddies to the smallest scale of motion, and to resolve all of those things, the computational cost is really beyond, computational expenditure is really beyond the capacity of basically gigaflop computers. Okay, so what can we do about that, right? What do we do about that? Well, what we do about that is to basically, we cannot solve all motions available. So we either incompletely solve the low wave number modes or the high wave number modes, really as simple as that. So we do take some measures of that. Before I get to that, let me sort of discuss this a little bit, because depends on what I will ignore, how many wave numbers I will resolve, how many I will not resolve, which one I will model. It should be based on at least some physics of what the turbulent flow has, right. So we need to look at that. So that's what I'm going to do. All right, now so let's just say here, since I talked about this, okay, the reasonable lower limit on L, right. Okay, so I should write that here. So domain size L, right. So we are looking at domain size L, grid spacing S, right, time stepping delta t. Okay, so L, so essentially L is equal to 8. Okay. Now this L11 is essentially integration scales. I'm going to briefly describe that in a bit. Okay. Right. So integration scales, which basically, so I'm going to just talk about that. Okay, which essentially boils down to, right, K naught, if you remember, is the lowest wave number. So the wave number space is essentially that is equal to, right, this, right, where K naught is lowest wave number, right. Let me also define what I'm talking about, wave numbers. So L11 is essentially integration scale. Okay. Let me just write this first. Now wave number okay is the number of wave cycles per unit length okay. Lambda is your wavelength. Okay, that. Okay, so now coming to the integration scales. Okay, now this L11, right? So this L11 is a characteristics of the is a characteristic of the larger eddies, right? And it is a length scale and it grows with time, right. So L11 is a characteristic of the larger eddies, okay. It grows, it is a length scale and it grows in time. Okay. Now, we've talked about the isotropy, the turbulent being isotropic, right? We've talked about that. Now, this so basically we can have the modes of motion in any direction, right? We can have the modes of motion in any direction, right? So we have to decide then how many directions do we need to completely define the motions happening in the dissipative range or the energy containing modes, right. So, so that becomes important, right. Now, this is an integral length, this L11, right, which is essentially in the longitudinal direction. Now, we need, right, due to isotropy, right, isotropy, we basically use two functions, right, two scalar functions f and g, right, f and g, right. are used to correlate the velocities u and v, right, at two different locations. Right, and due to isotropy, this f and g are independent of x. Interesting, right? So, how do I write this? Okay, so now due to isotropy, f and g are independent of x. So, essentially what I am saying is we have two scalar functions, right. So, to connect basically the u component of velocity, the v component of velocity at the two different locations, right. So, and due to isotropy, this is independent of x, right. So, then right, L11, right, is a length scale. So, basically I am going to integrate, right. So, this length scale, right, is equal to, right, this is the length scale, right, where this r, right, is equal to, right, this, and this k is a wave number vector, right. This I think we have done earlier, right. So, essentially what I am saying is that this is the length scale I need, right, to, so f, right. So, we use this f and g to correlate the velocities, right, at two different locations, right, which are independent of x. So, then I essentially L11 is in the longitudinal direction, right, where I do this, and that's all, right. So, you can see that f and g are essentially non-dimensional. So, this f, okay, before I do that, I also have the transverse integration scale, which is nothing but, if you have not guessed already, right, g, and this is also interestingly that, right, and also that, right. So, that is essentially the L11, right. So, in this basically what is happening is we are looking at, so I need to know that how far I need to integrate, right. So, to get a correct picture of all the motions, I want to cover all the motions, right, and if I cover all the motions, only then I will be able to make an assessment of the energy, and hence then how that energy is cascading or how is it dissipating, when it is dissipating, you know, that's the kind of information I am trying to get. So, then what is the length over which I should integrate? So, this is where what we are saying is, okay, now first of all, the turbulence is isotropic. This is to make our lives easier, right. So, we do that. So, based on that, we have two scalar functions, right, which will correlate the velocities at two different locations, right, and then we define these length scale integration length scales L11 and L22. So, this is in the longitudinal direction, and this is in the transverse direction, right. These are essentially the length scale. So, So therefore, when I say that in DNS the domain size, okay, the lower limit on the domain size, this is the domain size, that it has to be the lower limit, it has to be a minimum of 8 times the integration length, right. Only then I will be able to account for, you know, all motions, right. So 8 is the essentially the integration scale. Okay. All right. So the minimum length, minimum size of the domain has to be a minimum of 8 times of the integration scale. Okay. Only then we should be able to cover everything. Okay. Now, okay. Before I sort of, you know, look into that. Okay. Now let us look at 2 pictures now. Okay, 2 plots. Yeah, I guess. Okay, what we will do is look at this first. Okay, now that we know. Okay, let me just sort of go back a little bit. I think I wrote that here. Yeah. So the lower limit is on the domain size is this, which boils down to, you know, k naught. This is the minimum wave number, which boils down to like 0.8. Right. Now, how reasonable this is and how did I get this, right. So, that is why we are going to look at some of these plots. Okay. So, if I look at this plot here, now what you see is this is a result, this is again I am reproducing this from the book of Pope. So, you can see it is figure 6.18, I think this is page number 241, yeah, so I think the 241, I think that is what it is. Okay. Now, if you look at this, okay, now let us say here, okay, so the peak, right, the peak of this, the energy peak of this spectrum, right, energy peak of spectrum comes around here, right, which is basically wave number space. This is about say 1.3, right. So, this is the peak, right, this is about 1.3, right, and that, and if I take another point here. So, if I take this point 1, right. So, if I do this, right. So, about, as you can see, right, about 10%, right. So, this one here less than this, okay. So, about 10% of the energy scales is less than when k L11 is less than 1, okay. So, what I am saying is for k L11 less than 1, you know, 10% less than, so 10%, about 10%, you know, if I see here, right, okay, is less than 10% of the energy exists, you know, for wave numbers which is less than 1, right. Therefore, for our case, when we have we said the minimum length scale that we have is 0.8, right. So, which will be about somewhere over here. So, it would be around say 5%, right. So, this is right. So, KL1 is about 0.8. So, that means that 5%. So, we said that our minimum length will be 0.8. So, what this is basically telling us, so that if I do take that length scale, right, if I do take 8 times the integration scale, right, that was the domain size, which basically boils down to, in the wave number space, k naught L11 to be about 0.8, right, which is what we did. Now, then if I do that, so we said now the minimum length will be basically this much, 0.8. So, in wave number space, if that is 0.8, that means I am still losing out some of the energy containing modes, right, and how much is that, which seems to be about 5%, right, which is what I am seeing from this plot, right? I see that my peak of the energy peak in the spectrum is at about a wave number of 1.3, right? And if it is 1, so for wave number 1, so anything less than 1, there is about 10% of it, right? So I have 10% modes, and for our given limit, we will still miss out on about 5% of the modes, right? Okay, so okay. All right. So that is so essentially we will not be able to resolve those modes, right, which is about 5% of the total. So we're trying to see how much is, you know, worth. Okay. All right, that, and then let's see, we have, okay. All right. Now here what we are going to look at is the, again this is a plot, right. So this is the dissipation spectrum, okay, which is the this is the dissipation spectrum, right. Again, this is produced, I am producing this from the book of Pope, okay. So K eta. Okay. Now here, okay, what we see is that okay. Now let me just go back here and just talk about this a little bit. Okay. So we've talked about the you know, the integration length scales. Okay. So okay. Now, so like we said, you know, the resolution of the dissipative modes, right, which are the smaller modes. So these, for these particular this particular length scale, you know, we devise, you remember we devise specific length, velocity and time, and that was exactly the Kolmogorov length scales, right. So resolution of the smallest dissipative motions right are characterized by Kolmogorov scale and that was eta, right, eta, right, and it requires sufficiently small grid spacing, right. Okay. Or sufficiently large wave number okay. So essentially what we are saying is we have a certain space where we have motions going on, and these are very small, right. So for me to capture, you know, these motions, right, I should make sure that I capture as many waves as possible, right, hence this sufficiently large wave number thing, that is what we are saying, right. So therefore I should scan a you know, a part of that you know, spread or section or domain in such a way that I am able to capture the, you know, largest number of waves possible. So sufficiently large wave number, right. So each of these waves are small motions, but I want to capture as many, but then these motions are random and different from each other. So uniquely, and they are unique. So I need to figure out how those fare, how will I do that, right? So, my sufficiently small grid spacing, so I don't miss out on, yeah, so I don't miss out on the, on a wave just because it's small. So, if I have a small grid space and there's a little bit of turbulent behavior going on there, I want to capture it. I am not going to say that, oh, that's too small, it's all right, we can go up to this height. So, we try not to do that. So, that is something we would have done if we did just DNS, but it so happens that the computational cost is too much, and hence now we are talking about this, that what is the best way to deal with it. Although I know that I would want to pinpoint every little motion that is there, right, but practically it is becoming a little complicated. I am not able to do that. Then what do I do, right? So, essentially we are saying that it requires a certain, so in here what I have written down, sufficiently small grid spacing, which is delta x by eta, or sufficiently large wave number space, which is this, right. So, if you see now if I go back to this one, right, if you see k eta, right. So, this is basically the wave number space, right. So, if you see beyond 1.5 here, right. Okay. So, if I go here, so if you see, right, so beyond 1.5, right, so the dissipation seems to be negligible. So, I do not have much stuff going on there, k eta. Okay. So, therefore, a good resolution would be, this could be a good resolution to resolve the smaller scales. So, what this basically then, what do I mean by this? Now, when I say that, all of that, so this boils down to, so this is something, this, so let me write that inference. So, inference from that plot that we just saw. Okay. So, the inference from there is, or let me use this, okay, that dissipation spectrum, okay, negligible, right. So, hence this could be a good resolution to resolve the smaller scale. So, in physical space, right, this boils down to, in physical space, then, right, delta x by eta is equal to this, right, which is, I am sorry, so, this kind of looks a little large actually. The delta x is a minimum 2 almost double the Kolmogorov length scale eta, right. Now, okay, you see, therefore, we have, so ultimately, so what we are talking about is, okay, is two things, right. Okay, before I do this, let me also talk about the Reynolds numbers, because this is highly dependent on the Reynolds number. So, the higher Reynolds number that you need to get up to, right, will also determine the size of your domain and essentially the size of your, essentially the computational cost. Okay. What do I mean by that? Okay. Now, so the length scale characterizing large eddies, okay, let us just write that. So, here this is L, and we have been using this L earlier also, and this is like when we were describing the Kolmogorov scales, we said something got L plus, and we said this is close to the domain size. That was the large eddy size, and that is close to the domain size, right. So, here also we have said that this domain size is about 8 times the integration scale. So, the length scale characterizing large eddies basically is L, and this is something which is given by this, right. So, wave number and the dissipation constant, right. Then turbulent RE, okay. So, I am going to write that as this, right, that is equal to right. So, this is equal to yeah. So, this is essentially for the larger eddies, right. So, we need to look at, so the what is happening here is the length scales are far apart, then the wave numbers are far apart, right, and now we are seeing that even the Reynolds number is far apart. In the sense, in order to completely resolve a turbulent flow in a given domain, the length scales vary considerably, the wave numbers vary considerably, and the Reynolds number vary considerably too. Okay. So, and that is essentially resulting in excessive computational cost. Okay. Then the microscales then, right. So, microscales are then given as, so microscales then the smallest basically, right. So, I am going to just define that, okay, this which is equal to okay, eta to the power 2 by 3 and L to the power 1 by 3. I am sorry, it has gotten a little congested. Okay. Then let me just write it here itself. Okay. At high RE, so at high RE basically this lambda g that I have written here, okay, that lies between eta and L. Okay. So, at high RE, okay, lambda g lies between eta and L. Okay. And so, microscale, so this is the Reynolds number that we will be looking at. Okay. So, the smallest Reynolds number will be right, this makes sense. Okay. Right, UV Vd by mu, right, Reynolds number, velocity, length scale and coefficient of viscosity, right, and this is actually equal to that is an important result. See, so for a so to resolve a turbulent flow completely, we need to look at the space, the wave number space, the physical space, the wave number space, and also Reynolds numbers. So, Reynolds numbers will also vary. Okay. So, in that case, right, I think, so let me just say that so we have two considerations, right. In the, so when we started out, what did we say that let's just say resolution requirements, right. We talked about the domain size. We said what should be the domain size, what should be delta x, what should be delta t. So, and then we started looking at it. Okay. So, now let's just say that what our considerations are. So, our considerations are that L by is equal to 8, right, and right. So, these are the two conditions, right, which essentially determine the necessary number of Fourier modes, right. So, total number of Fourier modes is basically given by cube, right, as a function of Reynolds number, right, and this n is essentially the number of modes required in each direction, right. So, total the number of modes required in each direction, right. Now, then here, so this computational cost, right, computational cost actually increases steeply, right, as right, or that is quite amazing. You see, right. So, the more number of small scale or micro scale motions that you need to resolve, the Reynolds number is going to go up, right. So, pretty much so that is why, right, like I had said at the beginning, this, so it is almost impossible with gigaflop computers to go beyond an RE lambda of say 100. Okay. So, yeah, I am not going to write that. So, essentially I do not have a sufficient computer to do that, okay, right. Okay. So, okay, I need to do something interesting here. So, I do not think I will be able to finish, but let me kind of start. Okay. So, now that we have looked at the two, the figures also we have looked at. Okay. So, essentially when I said that we are going to use L, so this whole thing L by L 1 is 8 and all that. So, I mean, how did I come up with that? So, there is some experimental results to look at, and that is where I make my inferences from. Okay. All right. Now, so essentially what I am going to do now is now drop my domain, right. So, let us do that, let us do that. Let us see if I can do a good job today of this. Okay. Okay. So, this is my domain. Okay. Okay. All right. Now, this domain is basically 2 times k max. I will get to that. Okay. So, okay. So, let us go there, and I am basically going to draw not a bad job, right. Okay. So, this one, right, let me draw that. Okay. And let me also draw this. Okay. Okay. So, here essentially this thing this is k max and this is k max. Okay. Right. So, you can see that this radius, right. So, this here is, let us just say r. Okay. Here is Okay, I'm going to write it here is equal to K max. You can see that. Okay. Then next, let me draw another circle here. Okay, and here this R is equal to and finally I am going to do this, right, and this R so this R is equal to right. So, essentially what this is the okay, this is a domain, this is a domain that I am looking at, okay, of isotropic turbulence in wave number space. This is a wave number space, we are trying to solve DNS, right. Now, so this is this, right. Now, now K max, let me write a few things, okay, just jot down a few things, which is what we've. So, essentially this is my domain, right. So, clearly which we have learned, so around if more or less K max, this is what we had said, right. So, the minimum space, if it is if I draw up a domain which is K max eta is 1.5, right. So, only the modes within this sphere, right, within the sphere of radius K max are dynamically significant. So, only the modes within the sphere of radius K max, okay, are dynamically significant, right. So, that is what we are looking at the modes. So, therefore, this is my domain, right, and in this, but the problem is even if I say that, so which is what I have drawn up, but even if I do this, I am still sort of I do not have sufficient computer facility to do this, right. So, I am anyway sort of restricting the domain, which I am doing, right, and I am looking at dynamically significant waves, but still I do not have sufficient computing capacity rather. So, you know that the dissipative range is between K max and this R K of d I. So, this is the Kolmogorov scales which we have learnt earlier, right. So, the dissipative range is essentially between K d I and K max. So, what region are we talking about, right. So, right, this is the region we are talking about. Right. So, this is the region which is the dissipative region. There you go. Okay. So, this is the dissipative region, right, and K d I, okay. Now, let us just write that here actually. K d I is this, right, which is the wave number of the highest dissipative motions. Okay. So, KDI, so this is the wave number of the highest dissipative motions. Okay. So, now within this KDI, so within this sphere now, okay. So, within this sphere here, I didn't know that I couldn't do anything else, okay, no problem. Okay. So, this is the sphere that I am talking about. So, let us just say this sphere, right. So, within this sphere, which is right. So, radius of the sphere, the energy containing range, which is the inertial subrange, right. So, the inertial subrange exists, right. So, let us just say here, okay. So, this is the location, right. This is the here the inertial subrange exists, right. So, here inertial subrange exists and this one, right, contains the peak of the energy spectrum. So, we saw that picture, right, we saw that plot, we saw this plot and we did see an energy spectra here, energy maxima, we saw the energy maxima, right, and how many, etc., the length scale, etc. So, we did see a peak here. So, this is how the energy is. So, now interesting. So, I think I should point out essentially, so this is the distribution of the energy. So, that is why we basically saying energy spectrum function. So, this is the energy, how it is distributed over the space and how is that, this is a wave number space, right. So, we are looking at energy, right, and we see that there is a peak where the wave number is about 1.3, right. Okay. So, the energy spectra, so the maximum, the peak of the energy spectrum is actually right here of of radius where it is Ke. Okay. So, let me stop here and I think we will sort of talk about this in the sense that now that I have an idea of how the energy spectrum is distributed, etc. Now, what what is that, does that arm me or can I sort of tweak DNS based on that? I think that is what we will try to do next class. Okay. So, I will stop for now. Thank you.